protein synthesis, transcription, and translation model by the people on the page.
The location of protein synthesis is in the nucleus. It uses the nitrogen bases, adenine, thymine, guanine, cytosine, and sugar groups and phosphate groups of a nucleotide. The first step of protein synthesis is initiation of transcription. At the promoter of the genetic code, also known as the starting point of RNA synthesis, transcription factors meet the binding of RNA polymerase to the DNA sequence, then unwind the two strands of DNA apart. The binding of the RNA polymerase is also known as the transcription initiation complex. In the next phase, elongation of RNA polymerase begins laying down RNA complementary nucleotides on the template strand in the 5' to the 3' direction. However, the RNA polymerase replaces the thymine with uracil. The new RNA molecule begins to peel away from the DNA template when the RNA polymerase hits the terminator sequence proteins and cuts the RNA transcript free. This released transcript is also known as the termination step. The pre-messenger RNA leaves the nucleus, and there are a few modifications after transcription on the 5' end.
A guanine molecule known as the 5' cap is added on the 3' end, and the enzyme attaches 50 to 250 adenine nucleotide, known as a poly A tail. Once these modifications are complete, the mRNA is now mature and they exit the nucleus and enter the cytoplasm for translation. Before this step, RNA splicing has to remove intron, the non-coding molecule, from the RNA gene and replace it with exons. The coding molecule, the initiation translation, is when a small ribosomal unit formed by rRNA binds to an mRNA molecule in the binding sites of protein.
This recognizes the nucleotide sequence for the start of the codon. The initiator tRNA anticodon, UAC, which carries the acid methionine, then base pairs with the start codon. The large ribosomal subunit then joins with a small subunit and forms a translation initiation complex using energy released from GTPs. Once joined, the initiator tRNA takes the P site to the next phase, elongation. It begins with an amino acid activation called aminoacyl tRNA synthetase that joins an amino acid to the tRNA. The active side binds the amino acid, and then ATP loses two phosphate groups and binds the AMP to the amino acids. The tRNA that displaces the MP and covalently binds to the amino acid. The amino acid is released by the enzyme to form aminoacyl tRNA through a process called codon recognition. Next, the anticodon aminoacyl tRNA base pairs with the complementary mRNA code on the site and also provides energy that increases accuracy of this step.
Now the molecule is on the large level. Also viewing using the Kep transfers for the formation of a polypeptide bond between the new amino acid and the egg with the carboxyl end of the growing polypeptide on the P side. The ribosome then moves the tRNA on the P side to the E site. The tRNA of a site to the P's on the E side is released since it isn't in the exit site because there is a tRNA on the E site. This translocation allows them to shift over at the cyclase base on the codon. A protein known as the release factor binds directly to the stop codon. The A site is also between the tRNA amino acid, which causes the release of the polypeptide to the large subunit to something that's been disassociated, and the cycle repeats.